Okay. Yeah, hi, I'm Max. Welcome to my presentation towards Neural Debugger for Python. This was worked on during my internship last year together with Jonas Gehring, Yannick Kosen, and Gabriel Sünneve in the CodeGen team at MetaFair in Paris. So, 6 months or a year ago, coding looked like this left image that I show here on the slide. We basically were using for this an IDE, in this case, Visual Studio Code, and the debugger to debug the test cases that we write ourselves and debug the program that we're about to write and find some bugs in the program. Now, with this recent progress in the past 6 months or a year with coding agents, this has a major impact to any workflows, to the workflows of software engineers or anyone who is writing a lot of code during his work. And these incredible capabilities of Claude or Codex demonstrate that when we wrap these models into agentic harnesses, these current coding models then can write complete code bases, detect, locate, or fix bugs in existing code bases, or even design and propose new features. So, as a result, today, instead of using the debugger so often, you can more and more just describe in a natural language what you want to do, the edit that you want to do, the new feature that you want to write, and then Claude goes off and does that on its own. And by doing that, it uses tools to find and execute relevant parts of the large program. It reasons about specific designs and their trade-offs. You can have a design conversation with them, and it is a very talented engineer, so to say. And also what it does, it understands the program flow without executing the program. So you can ask it about the program and it can really reason about the execution. And this is also the topic that this work falls into. So the main topic of this work is basically teaching the LLM semantics of code with execution traces. And execution traces are records of program flow, variables, and program transitions during execution. And there are also other approaches to expose LLMs to execution data, mustn't be execution traces. For example, you could include feedback, and that which is already done, of test results, error messages, or runtime or shell outputs into reinforcement learning loops. Or you could set up iterative generation loops, similar to this agentic workflows where the model executes it, gets some feedback, and then execute and modifies the program and executes it again. However, this work, we focus on training large language models directly on execution traces. And I said already, these are records of variable states and control flow transitions of executed programs. And execution traces were used in several previous works already, but one prominent example I want to highlight, which I was also involved during my internship last year, was the code world model. So here, the code world model, CWM, is a 32 billion parameter coding model that is trained explicitly on large amounts of execution traces during its mid-training. And as a result, the CWM can simulate line-by-line execution of Python programs, which effectively turns it into a sort of neural interpreter. So you can give it a function, you can give it arguments to this function, and then the model predicts every execution step. And now if this function, for example, has 1,000 iterations, it will predict every of this 1,000 iterations because that is what it has seen during training. And as a drawback, this can lead to very long sequences in the case of very long loops, for example, or large objects, which limits the execution prediction to shorter programs. And also, it does overlook how human developers inspect programs. So I've shown the example earlier with debugging the test case with the Neural Debugger. So here we would not step through every line. We would set a breakpoint at the very interesting line shortly before the bug, or we suspect the bug to be, and then step only through a few lines. This is not how it is done in CWM. And neural debuggers should overcome this. So the main idea of a neural debugger is and that we introduce with the concept here is that we build large language models that can simulate program execution while providing core functionalities of debuggers. And these core functionalities are these debugger actions. And the main idea here is to overcome this issue with this very long execution traces and to make the debugging more similar to how a developer would debug a program, is to interleave the program states in the execution trace with actions that are inspired by traditional debuggers, such as step into a function, step return, step to the return statement, step over a function, or setting a breakpoint, and then predict the program state at the breakpoint. And this enables the model to control which part, or either the model or the developer to control which part of the execution trace the model should predict. And this has several advantages over traditional debuggers. We can, for example, simulate execution for non-executable or partially specified programs by letting the model predict the outcome. We can also have more efficient reinitialization of program state and execution context through prompting and regeneration instead of restarting the program. Just think of debugging a training loop, which usually has some setup to do before. And then when you want to come to the important point, it takes some time. This would be faster with a neural debugger. And in addition, we introduce also approximate prediction of inverse execution, which is typically ambiguous. So if you have 1 plus 2 is 3, there are many different variables that equal to 3 when you sum them up. Actually, infinitely many. So what the model can do, it can infer or sample plausible preceding program states or inputs. On the other hand, we could also use these neural debuggers in agentic workflows. They could serve as learned world models for simulated debugging environments. So for now, we see in Cloud Code that it executes some command, but it could actually in the background also simulate just the execution, which might be even faster. But that would be just one use case. And the other use case would be that we can Claude enable to control our real VS Code debugger because it now has seen this kind of interaction during training already. However, this work is only validating this concept of neural debuggers. We have not applied it yet to such agentic workflows, but leave that for future work. And with that, I'm coming to the outline. So at first, I will start with a background on Python execution traces. Then I will introduce this neural debugger data pipeline, where we formulate the neural debugger as MDP, and then go through every step of this pipeline that I show here, step by step. Finally, I will show experimental results that validate that a neural debugger can predict program flow and program execution. And at last, I will point out in our conclusion, limitations, and future work. So before we can train models on execution traces, we need to understand how Python execution traces actually look like. So I suspect execution traces in other languages would be similar. So this is more the concept of what are execution traces. So in Python specifically, program execution is organized as sequence of frame stack objects. And a frame stack object contains current local variables, local and global variables. It contains the current source line and the current execution event, which could be a line event, a call event, a return, or exception, for example. And typically, these frame stack objects are stored as a call stack. So during execution, when you are in a function, you are at one level in the call stack. When then you call another function, you go one level deeper. And when the function returns, you go one level up. Typically, we see these call stacks when there is an error in the program, in the error message, or even when we debug through the program, we see that call stack. And Python also provides access to these frame stack objects via a trace function. So this sysset trace function basically sets a custom trace function which records or can record these frame stack objects. Typically, traditional debuggers are implemented through these trace functions. And in our case, we use this custom trace function to record the execution traces for neural debuggers. And here on the right, we just see two recorded stack frames. So here, for example, this is one stack frame where we have a line event, and we don't have any locals here. We have in the function main, and we are the source line return func1, 2. And here, this is a call event. We have the locals A, 1, and B. So this is how the raw data looks like. It's basically a sequence of dictionaries. So this is our source trace. What we do with this source trace, we want to create execution traces that we can feed into the model, and that is what the Neural Debugger pipeline does. And to have to formalize this a bit, we formalize the debugger as an MDP, and this is motivated by the fact that a debugger is basically a program that holds the state of the program that is being debugged and receives actions that control the program execution. So it's basically, it has a state, it receives actions, it modifies the state. And this is the motivation for formulating it as Markov decision process. And the Markov decision process is typically given by this tuple of state space, action space, transition model, reward, and initial states. And these map natively to the Neural Debugger. And I will show you now. So S is the space of the state space of program states, and here we see the layout of the program state, and also contrasted to the CWM. So here, the CWM model, you see the state was the event, the locals and args, and the action was the source line. Now this is different in the Neural Debugger. We consider the event, the locals and the args, and the source line, which serves basically as a program counter, or maybe basically pointing at the current point of execution. This is the state, and the action is then the action space, which is the set of available debugger actions. Step into, step over, step return, breakpoint, or continue. And then the transition dynamics, P, is the transition dynamics steered by the debug program. And then there could be also a reward function. However, in this work, we focus only on learning this transition dynamics, learning a world model of the Neural Debugger, and we don't specify any rewards for now. Later rewards could specify a specific debugging behavior, for example, as quickly as possible, localizing a bug, for example. But we don't do that in this work. And then S null as 0 is the set of possible entry points. So with this formulation, we basically build something that we call a state tree. And the idea behind this is we want to define a model for the transition dynamics. And now you will see why we use the state tree for that. So on a high level, let's go through a very simple example here. So we have this code which consists of these three functions, and these are the main function calls this function AB, which sums basically with another function two variables. When we record this execution of this program, we get the following execution trace, and the different functions are marked by the different shades of gray. And then what we do with this execution trace, now I don't show the local variables, only S, which is the source line. So we can build a state tree. And the state tree basically reconstruct the call stack by tracking the sequence of call return events. So we see call, 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 we go level deeper, level deeper, level deeper, and then return, we go the levels up again. And then we see that this, when we organize these lines in a tree, where basically the program states in a function are the childs. So let's look at, for example, this gray function here. We see that the program states within this function, this func function, are the childs of the line event that calls this function. So, and this basically resembles the tree data structure. And we also see that the depth of a node in the tree corresponds to the depth of the call stack at the given program state. So this is a nice similarity. And we will now use this state tree to define the transition model of the Neural Debugger. So the transition model of the Neural Debugger is defined by different traversal rules on the state tree. So for example, so we have this state tree, we can see different. So these black arrows actually show the sequence when we always do step into. So step into, we go to the next, we step into, we go to the next, we step into, and so on. But at this point, we could, for example, just also step to the nine, the node 9. And also here we could from 3 to 8, which would be basically the step return. So what this means is basically that each debugger action results in a transition from a starting node to an end node. So just as what it would look here in the execution trace state tree. So here the step into steps into the function. When we have step over at the function 3, we would basically step to 7, which means we don't step into the function, and so on. So this is a nice similarity or correspondence that we use to define the transition models, the transition model of the neural debugger. And we see that different actions have different starting and target nodes. So with this, this processing of execution traces as state trees also enables inverse execution predictions and inverse debugging. Since we have the state tree already basically in memory during data loading, what we could do is basically we could just reverse this state tree. So here you see we start with 9 and end with 0, but have similar actions basically. So there are some technical details that we need to be careful about. Basically, how we how when and how do we show the local variables. But I want to go into these details. But on a high level, what we do basically to enable this inverse execution prediction is that we duplicate line events with function calls with a special event type. Here, for example, this inf line call. And in this line call, we basically don't show the local variables because they would actually already include the return argument or the return values. So yeah, you need to be careful here. That's the bottom line. We also disable breakpoint. But the other actions such as step into, step over, or inf step call, which is basically the step return, are similar to the forward execution prediction. So we could basically reuse all the state tree logic for the reverse state tree prediction, but need to be a bit more careful about how we show the local variables. So this was the first step. So we have the source trace, we built the state tree, which resembles the call stack. And then the next step is basically to get trajectories out of that. So for now we have a tree, but we cannot or very hardly feed this tree into the model. So what we do is basically from each state tree, we generate debugger trace trajectories by sampling random actions. And the benefit of this is now we have, when we have like one state tree, one execution trace, we could basically sample many different instances of this state tree by sampling different random action sequences. So by that, it's also a form of more of data augmentation, basically. So for this random action sampling, we use a mixture of categorical distributions, basically to ensure diversity and sufficient trajectory length. So you see here, we use a mix between a policy that samples only 50-50 from step over and step into, and one policy that has basically full action coverage. And then here you see already the statistics of this action sampling. So we have two different data portions: function level, which traces only functions, or repo level, where we trace the tests of a full repository. And you see that even though the characteristics of these functions are very different, the actions, because we use the same action policy, have the same or very similar statistics. So on average, basically, we have 8 to 9 actions in one execution trace. And then you see, because step into is and step over, they are more represented in the trace than the step return and the breakpoint action, because these have higher probabilities in our action sampling probability policy. Okay, so this was the second step. We have built the state tree, we have sampled a trace trajectory, and now we have this sequence that looks like on a high level like this schema here above. So the three debugger trace trajectories are state action sequences. They start with the code in their context, and then we start with the initial state. We execute an action, we modify the state, and so on. And remember that the state basically contains the event information, the locals or args dictionary, and the source line. And actions are these debugger actions. So now in our format, basically we need to find a format that tokenizes these state action sequences into a sequence of tokens that the model can process, basically that so that we can use it with any off-the-shelf large language model. And for that, what we do is basically we introduce a structured neural debugger grammar or language, a formal language for that. And that basically consists of the fact that we mark the state and action sequence with special separator tokens, and also introduce special tokens for each action, for example. And then we need to think a bit about how can we represent the locals, because we've seen the locals are basically dictionaries of the variables. So it's a key value mapping, basically. What we do is basically we serialize these locals as a JSON in JSON format. And then because we don't want to have our sequence being very long for predicting local variables that do not change from line to line, we basically only predict variables that have changed, and insert this placeholder to indicate omitted unchanged entries. And then we convert also arbitrary Python objects, for example, data frames or tensors, NumPy arrays, which are a bit challenging for now with their standard wrapper methods. I think there could be also much better methods, or like future work should develop better serialization and better arbitrary Python object representations. And as a result, I can show you here like a very simple example of the a tokenized trace. So for now, I don't show the tokens; these are still the characters. But these arrows here, smaller and larger signs, indicate the special tokens that I was referring to. So here we see that the begin of text token, and here this marker that trace context start. So this is the context, the code, the function that we are about to trace, or that the neural debugger predicts in the end. And then here in the format, we have the first frame. Frame sep is the frame separator token. Call sep marks the call event. So we start here with the entry point, which is the main function. There are no local variables, so the dict is empty. And then this action sep is the step into. So we step into the function. We are here at the line return 5, and then we step into again, and we are here at the call event of this function. And now the argument, because we have here 5, is locals dictionary contains the single digit 5. And then, so this is actually a prompt, which I will explain later. We could have, for example, a breakpoint action that directly returns the result. And then the model would predict, so here was the prompt, would predict line sep. So we are now at this line. It predicts the single digit is still in the context, in the locals variables. And the result now is this list, which contains basically all numbers from 1 to 11, except 5, because this is what the function does, and also the iteration count of 10. So this is how the execution trace basically looks like. And you see this in the leaved local variables or state and actions. So frame sep and action sep is one state action pair. Okay, so this is the full data pipeline. We've seen how we can feed execution traces in the neural debugger format into the model. So now let's look at some experimental results. And here we are mainly interested in validating basically this concept. And here we want to understand how does fine-tuning the code world model, the 32 billion parameter model, compared to pre-training smaller transformer models, which are specialized to these neural debugger traces. And then what are prediction accuracies of these individual state elements, the line event, the source, and the locals. Basically, where do neural debuggers make errors? And finally, how well do these debuggers perform on like input-output prediction downstream tasks, as this is the closest downstream tasks to this neural debugger data. that one can think of. Okay, so our experimental setup, we train neural debugger models by fine-tuning on the one hand the CWM parameter, a 32 billion parameter model, and on the other hand, pre-training small 1.8 billion transformer models. The fine-tuning is done on 50 billion tokens debugger trace data only, and for the 1.8 billion transformer, we train either 50 billion or 150 tokens with different data mixes, so trace data only, web data, and code data. And then how does our execution trace data set look like? We use basically the same as for the CWM model, but just process it with our neural debugger data pipeline. It consists of a large portion of function traces, repository images, and code contest solutions. And then the final debugger trace data set consists of 15 billion repository level tokens and 100 billion function level tokens. Both include already forward and inverse state prediction, neural debugger execution prediction. And now when we look at some statistics, what is the difference between function and repo level? So earlier I showed a similar statistic, but with the actions. Now I show the event the event counts basically per on average per execution trace and also the number of tokens. So we see that in yellow is the repo level, which is this traces that are traced from executing the tests in a repository, are much larger, much longer. So they have on average 3,000 tokens, while the function level only have 360 tokens. They contain more call and return events, which leads to the fact that this repository tests have deeper call stacks, so more call and return events and fewer line events. And also they contain more exception events. And why are they so much longer? Also mostly because they have more complex arbitrary Python objects, which also increase the length of the execution trace. Okay, so now let's look at this first experiment, fine-tuning and pre-training neural debuggers. So here we compare these 4 different models, basically, or more than 4, but 4 different setups. So we train the 32 billion and then 3 different instances of the 1.8 billion tokens, 1.8 billion parameter model. We train either on 50 billion or 150 billion, and we distinguish between trace only, 50% trace data, and 33% trace data. And then we categorize the results. So these show the evolution of the performance over training. So we see the number of tokens on the x-axis. On the y-axis, we see the exact match performance for the different actions. So here on the left, you see the step actions, which are like for the forward prediction on top and the inverse prediction on the bottom. So step into and step over in the forward, and here inverse step over, inverse step into, basically. And then each result is averaged over 800 trajectories from the function level validation set. I only show function level, but for repo level, it would lead to the same conclusions. And what we see is basically that the step actions are easier than the jump actions. So they achieve higher exact match performance when we compare the step actions to the jump actions. Same is for forward and for inverse. What we also see is that inverse prediction is learnable. So we get some decent performance. It's a bit worse than forward, but it is very good. What is also interesting is that we see that the gap between this inverse, between the 32 billion and the small model is very small, which could also be the fact that the CWM has seen this forward prediction already during mid-training, but not in the debugger format. But inverse, it has not seen. So here they basically start from the same point. And then what we also see, and I've hinted at it already, that the small models are good neural debuggers. So there's like in step into and step over, there's only a small gap after this training for 115 billion tokens with the small models. Only for the more complex jump actions, the gap is a bit larger. Okay, so we've seen that it works. We can train on it, and the model learns to predict execution. But where do the neural debuggers make errors? And for that, we only look at forward prediction for now. So here we again show the exact match matrix, and we do that by state component. Note that the state components here are the event, the locals and arcs, locals and arcs on the left, and the source line. And we see here that the source line and the event for all the actions, the breakpoint, step into, step over, are very predicted very well. So we are far beyond the 95% region. However, most of the errors are in the locals and the arguments, which makes sense because it's much harder to predict the outcome of the variable than what would be the next source line, basically. So here you have to predict the computation, basically. This is why it's harder. And then we also see that in the local variables, especially the jump actions like breakpoint and step return, it's there are the biggest errors, and there are also the gap between the 32 billion parameter model and the small model is the largest, because I suspect that this 32 billion model has just the capacity to do more computation within the model than the small model. So this could explain this gap. And finally, now let's compare it on downstream task on Crookes eval. For example, when we compare the input and output prediction. And here we see that the Neural Debugger model fine-tuned or the fine-tuned CWM model on Neural Debugger data improves over the original CWM model. So originally we have achieved 58.1 on output prediction, and now with the CWM fine-tuned Neural Debugger model, we achieve 77 or 83% respectively, depending on which action we use. Actually, you've seen this prompt before, which was one instance of the breakpoint prompt for the output prediction. So here you saw we put in the function in the context. We add some initial prompt that lead the model or step the debugger into the function, and then we directly predict the add the breakpoint action to prompt the model to predict the output directly without any intermediate steps. And what we also see with these results is that the gap is not too large, and the small models are actually, for their size and the amount of training data, very good on Crookes eval, which would rank them, I would say, I think in the top 10 on the current leaderboard, but the current leaderboard is at the time of GPT-4, so it's outdated. But for the size of the models, these numbers are quite good. So now I've said that for now we've prompted the model to directly predict the output. The last question that we wanted to ask is, how does the prediction accuracy perform for increasing prediction horizon? And what we did here is basically, so you've seen this earlier prompt where we directly added the breakpoint. But what we do now is we basically add a variable number of step into actions, for example, before this final breakpoint action. And for that, and there is, as a result, we get basically different prompts for one example, and we have a different number of skipped frames. So basically 1.0 is the first, the largest prediction horizon, which is the example that I showed before. No intermediate step into actions, but directly predict the output. And we see that here the performance is the worst. And for longer a prediction horizon, we see that here on the x-axis, longer prediction horizons on the right, we see that the performance drops in the exact match prediction of the outputs. And then what we try is we try different paths at k or exact match at k scores, and we see that this sampling partially mitigates this this drop. So this opens also new avenues for future work. For example, we could investigate the uncertainty of the model for predicting specific the outcomes of specific source lines, or predicting specific execution flows, and monitor the uncertainty on that. Also explore some inference time strategies to improve performance, as we see that sampling could improve the performance here. So with this, we've seen that the Neural Debugger concept is viable, and that it leads to models that are reasonably good on input and output prediction, and that they can very good predict the execution flow of Python programs. What we've not done so far, and this is one major limitation, is we have not applied it to agentic program repair, reasoning, and tool use with Neural Debugger so far. So I could imagine that during reasoning, we could, and that's actually something that we've tried with CWM already, but not with Neural Debugger. We interleave reasoning traces in reasoning with a Neural Debugger or with execution traces, and in that way encourage the model to use this execution trace prediction during reasoning. And there's more future work, for example, expanding and improving the data generation, expanding it to other programming languages. And as I've said, we've just used random action policies. We can either use expert policies or maybe make this random action policies more informed about the execution. So for now, we could, for example, incorporate like syntactic information that there is a loop that we want to jump over the loop or so, or something like that. We have not done that. That's future work. And in addition, we could improve the inverse debugging. So for now, we predict only one instance, but we actually we could resolve this ambiguity by predicting feasible value sets, and also improve the metrics that we use to account for this ambiguity. We basically would need to execute every instance or every predicted instance at evaluation time and check whether this is a viable prediction of the model, since we have this ambiguity. And I've also mentioned that already. We could improve the better Python object representations, especially for complex data structures. So with that, I will conclude this talk. So we've seen that training on execution trace data enables the simulation of program execution with large language models. Neural debuggers is one concept that enable line-by-line execution of computer programs conditioned on common debugger actions, such as step into, step over, and so on. In this work, we formalized the Neural Debugger MDP, where states comprise where states comprise program variables and source lines, and transitions are defined by transversal rules on a state tree data structure, which we reconstruct from the program's call stack. Future work should integrate neural debuggers into this reasoning and agentic workflows. With that, I'm at the end, and thank you for the attention. And please check out the paper if you have more questions, but also ping me.